In this video, we're going to discuss heat, specific heat, and heating curves. So let's redefine the definition for temperature and compare that to heat. Temperature, as we've discussed in the past, is a measure of the average kinetic energy of particles in a substance. So the hotter something is, the faster it moves, and the faster it moves, the higher the kinetic energy. Heat energy is also called thermal energy, and it is the sum of all the kinetic energy of particles in a substance. Its units are joules or calories. So you've seen calories used in foods and nutritional information, and calories in that context is basically a form of heat energy that is located in the bonds in the molecules of food. Heating and cooling is the transfer of kinetic energy, and the transfer of energy doesn't happen randomly. Energy is transferred from hot to cold. So if you were to put your hand on a hot stove, the kinetic energy of the molecules on the stove are moving really fast, and they would lose energy to your hand. And so that burning sensation would be energy lost from the stove. So it's kind of weird. If you think about, like, if you open up a window and it's really cold outside, you think that the cold air is coming in, but in reality, the warm air inside is losing energy to the cold air outside. So it's important to know that temperature is not the same thing as heat. Specific heat is the amount of energy required to raise 1 gram of material 1 degree Celsius or 1 Kelvin. So here's a list of common materials and their specific heats. Notice, so liquid water is 4.18 joules per grams times degrees Celsius. So it actually has a much higher specific heat than water in the form of ice or in the form of a gas, water vapor. And so what these numbers mean is, in the case of liquid water, it takes 4.18 joules to raise 1 gram of water 1 degree Celsius. And this is why, as you notice, water has a really high specific heat compared to other substances, which is why it's so good at stabilizing temperature, which is one reason why our planet is habitable, because liquid water is a great stabilizer. It takes a lot of energy to heat it up and to cool it down. Your reference table has a list of specific heat for common metals on page 1. So if we wanted to look at or to determine how much heat is required to raise the temperature of a 600 gram bar of aluminum from 70 degrees Celsius to 95 degrees Celsius, we are going to have to use a formula. And in this formula, Q equals M delta TC of P. Q represents the heat required, or the heat lost, in this case required, in joules. M is the mass. So the bigger the mass, obviously, the more heat that's going to be required. Delta T is the change in temperature, and that's the final temperature minus the initial temperature. And you would multiply those two things together times the specific heat of the given substance. So in the case of the problem that we just looked at, when you plug everything in, so Q equals the mass, which is 200 grams, times the change in temperature, which is the final temperature 95 degrees minus the initial temperature 70 degrees, times the specific heat of water, which we saw 3 slides ago is 4.18. So this is the C of P, the specific heat. And it takes 20,900 joules to raise the temperature of aluminum from 70 to 95. It seems like a pretty big number, but joule itself is a really small number. So we a lot of times will use kilojoules, just like calories are a really small number. So when you look at nutritional information, it gives you calories, but really what it's giving you is kilocalories. So this would be 20.9 kilojoules. So let's talk about the energy required when melting or vaporizing something. Latent heat of fusion is the heat required to turn a liquid into a solid. And it can be expressed mathematically with Q, where Q is the heat equals the mass times the heat of fusion. And so for water, the heat of fusion is 334 joules per gram. So the bigger the mass, right, the more energy that it'll take to melt that water. Heat of vaporization is H of V, is the heat required to turn a liquid into a gas. So for water, to turn liquid water into water vapor or gas, it takes 2260 joules per gram of energy. So the equation is the heat energy required equals the mass times the heat of fusion. So let's look at, let's relate this to a heating curve. So on this heating curve, if this is the heating curve of water, we have heat added to the system, and you can see when the matter is in the solid phase, when it's ice, the temperature of it increases, as we talked about before, and then it starts melting. So at this point, all of the heat that's going into the system now goes into melting the ice. So from here to here, that heat goes into melting the ice. And the energy that it takes is the heat of fusion to melt that ice. So if you look on your reference table, heat of fusion for water on the first page is 334 joules per gram. So that means that it takes 334 joules of energy for each gram of water to melt it. And so once it's all melted, then that energy can go into heating the water, into raising the temperature. And at this point, we have liquid, all liquid, and then the liquid, part of the liquid turns into gas. And at that point, the energy that's added goes into transferring that kinetic energy, those molecules, from a liquid to a gas phase. So remember, that's the heat of vaporization. And the heat of vaporization, which is HF, is, if we look on our handy dandy reference table, is 2260 joules per gram. So it's a lot higher actually than the amount of energy that it takes to melt it. It takes a lot more energy to boil the water or to get it to go into the gas phase. So if I wanted to determine how much heat it would take to melt 200 grams of ice, then I could use Q equals the heat required equals the mass times the heat of fusion. So that equals 200 grams times the heat of fusion was 334 joules per gram. Gram is on top and bottom, so it cancels. And when we do that math, I've got to, of course, find my calculator. then I would just do 200 times 334 equals 66,800 joules of energy that it takes to melt 200 grams of ice. Now, if I wanted to boil that same amount of liquid water, then I would just say Q equals M times the heat of vaporization. Now remember, H, we use that abbreviation for enthalpy, and enthalpy is heat content, so it's the same H. And so that's going to equal 200 grams of liquid water in this case, times, now we're going to use the heat of vaporization for water, which is 2260 joules per gram, which is 2260 joules per gram. Grams cancels. And 200 times 2260 equals 452,000 joules, or 450 kilojoules of heat energy is what it would take. So if I wanted to cool it, then it would release that much energy into the environment. If I was to cool it from a vapor into a liquid, that's how much it would release into the environment. So you can now start on your classwork.